say I didn't do a mic check, so hopefully you're getting sound. It looks like you should be getting sound. And just as my Twitch page goes a little laggy. Good. Good morning. Morning, Vince. Morning, Brooksy. Who else is here with us this morning? Okay, that's good news. See Dice Case here. Jack, which could be Vince. Okay, anyway, so good morning, everybody. Hopefully I didn't break our rhythm too bad by taking the day off on Thursday, so now we're in the home sprint. We are on homework 12 of 15, I think, and then lab 13 of 16 officially. We have one sort of last big splash lab at the end. So this week, let me turn on my browser. Let's go survey real quick what we've got going. So this week we have, this is the week of April 28th, yes. Homework 12 this week and lab 13 this week. That's what, and then, so we're getting there. We're almost there. I know the school has said that we're just going to do a normal last week of class, but I'm not going to do that. I'm going to just finish my content. So I had already sort of made my plan for the rest of the semester before, for this online format before they announced that they were converting the finals week. So we'll just have our last sort of regularly scheduled 8:30 on that. I'll let you know well in advance. But just so you know, we're going to be done a day early during the last week of during finals week, which now is just considered the last week of class. But my plans don't need the extra day at this point. So that's just a heads up about that, and that's mostly, I think, to help myself and my attitude about the last few weeks. So we have this week, and then May 5, May 12, May 19. So we've got 4 full weeks, and then we'll have one final meeting. I'll change that time to show when that actually happens. But if we can just get through 4 more weeks and then one last day during the last week, then we will have done it. So I know this is challenging. This is morning, Dice K. This is the most challenging class that I've got in terms of getting people through it because of the hardware. So congratulations to you that you're still going strong and that you're managing to build the circuits and write the code and test the circuits, most of you, and get things working. So good on you for doing that, because this is not easy without having someone in the room who can come over and kind of look at what you've got. So good going for that. Okay, so what we're adding this week is how to do multiplication and division. This architecture course for a computer scientist, in my opinion at least, it's a lot about just having some sense of what's going on under the hood. So when I write X times Y in C++, just having some sense of what that makes the processor actually do. Some people consider useful information. I think I'm a better programmer knowing how to write some assembly, even though I rarely actually write assembly. I think just understanding how C++ high-level constructs have to be converted into the low-level assembly constructs, I think just makes me make better decisions as a programmer. So hopefully someday you'll appreciate that. I also use hex values a lot in my programming because it's such an efficient way to store and manipulate data. So hopefully that might be something that you have as a takeaway from this class. But I know for most people, they will always be left wondering, why did they make us do assembly? And that's the best answer I have. We do it because the CSUs and the UCs do it, and they do it because that's still the mainstream of computer science around the world, is to have everyone take at least one computer architecture course. Okay, so this week is mul and div. I'm going to move my browser over the top. We don't need this text editor stuff. So let's go hunt down these answers first, and then I will write a small experimental program, which you can just watch me do if you want to. I'm not going to do any of the lab today, but I will probably do some small experiments in assembly just so we can see what it looks like before we get to the actual lab on Thursday. Okay, so homework 12. Okay, so show the signature of a mol instruction and then describe the operation of mol and mol s. You may or may not remember it, but when we slap an S on the end of an instruction in ARM, that usually means that we want condition flags to be set, status flags. So if you put the dash S at the end, then certain status flags are set after the instruction executes, and if you don't put the S, then no status flags are set. Okay, so I'm going to bring this up in a different tab, but let's go look at the multiplication, and we want to read about mol and mol s. I'm not going to bother with all this lead-in text for now. What I want is this stuff right here. So there are 3 simple multiply instructions in ARM. Mol with one L, smol, which is signed multiplication, meaning when you want to multiply signed, i.e. positive or negative values, and unsigned multiplication. The one you use depends on the size of the numbers, and for large numbers, their sign. Okay, so the simplest one is mul. Mul multiplies 2 32-bit values and produces a 32-bit result. I like that, so I'm going to probably keep that. Now, when I say signature, what I mean by signature is how does the function set itself up? So this is the signature that I've highlighted here. That means how do you actually write the instruction? What does it look like if you were to write it? Now, when we say signature, we don't mean to actually write one. We just mean what would be the setup. So here's the instruction, and then we have the arguments, which is the destination register, and then 1 and then possibly 2 source registers. So that's the signature. I'm going to take that and I'm going to, well, let's just take that. That's fine. That's the signature of mol. It copies kind of messy, so I'm going to clean it up a little bit. No, it's fine. I'm okay with that. Okay, so that's the signature of a mol instruction. That's kind of how it would be set up. The curly braces mean optional pieces. So optionally, you can add the S to have status flag set, and optionally on top of that, you can add a condition code so that you can put it in an if-then block. The destination register is not optional. At least one source is not optional, and then an optional second source. So I'm going to do a couple of examples just so you can see what this looks like. So if I wanted to do, for example, R0 equals R1 times R2, then I would say mol, my destination is R0, and then I have 2 arguments, R1, R2. I'm going to scrub these samples, by the way. I just wanted to show you a couple of examples while we're working on it. And then we can speed up after we get past this first one. Now, if I wanted to do something like R0 times equals R1, then we're allowed to write that in ARM assembly as well, where if you only put 1 source register, then it assumes that the destination is also a source. So R0 equals R0 times R1, or R0 times equals 1. We might write it in C++. So that's what we mean. We can also do mol s. Right, that's what that's telling us, which means that after this instruction fires, the status flags would be set. And then we can also do something like compare R0, R1, if then equal mole equal. So that's the C part. Actually, you can't put hard values in there. Anyway, so I'm just sort of showing you that that's what the signature kind of tells you, the different setups you can do. You can also do a mole S. Not equal if you get the point. So we don't need any of that. I just wanted to show you for this first example that what the signature is showing us is that we have a lot of different ways that we could optionally set up this instruction. We don't need that for the answer though. We just need the signature. But I wanted to show you for this first one that all those curly braces means an optional piece and how that would look if you were taking advantage of the options. Okay, so now describe the operation of multiplication. So the basics of it is right here. Multiplies two 32-bit values and produces a 32-bit result. And let's see if there's any extra details we can pull to make that a college level answer. We've already sort of talked about all these options, but I think more importantly in terms of how it works is the extra words. So the values in the two source operand registers, that's Rn and Rm, are multiplied and the low order 32 bits of the result are stored in Rd. If Rm is not present, Rd is used as the second source. That's the times equals thing. The assembler prefers that Rm be used. Who cares if the assembler prefers that or not? We're going to write it however we want to write it. But one thing to note here, this is hard to see, but I'll try to trigger this situation. This part right here, the low order 32 bits. So what can happen, you can imagine this, if you multiply two 32-bit integers together, you may get a result that's way bigger than fits in 32 bits. That just can easily happen. You can imagine it with two 8-bit values. So imagine if you multiplied 255 by 255. Those are both legal 8-bit values, but that result never in a million years is going to fit inside an 8-bit register, right? So what this is telling us is that if your result is bigger than would fit in 32 bits, you lose all the high-end stuff. You just lose it. So that's something to keep in mind, that this instruction does not guarantee that you don't lose data when you multiply things together. But I'm going to take this paragraph and I'm going to use it too, because that sort of makes this a much stronger answer. And there's one other thing, which is none of this really speaks to mol S. So let's go see if we can find something that fleshes out mol S. Yeah, right here. So if the S is present, the negative and 0 condition flags are updated according to the result. So I'm just going to keep that first part, and then I'll let you sort of, I'll pause for a second. And I'm going to write it like this, because I think that's just sort of simpler to read. So mol and mol S both multiply two 32-bit values, produce 32-bit result, and then explaining kind of how the registers in the signature work. The lower 32 bits of the result are in the destination register. If Rm is not present, because it doesn't have to be, then the destination is used as the other source. That's the R0 times equals R1 example. There's a note here about the assembler prefers that Rm be used. Okay. The 32-bit result does not depend on whether the source operands are considered signed or not. So that's an important detail. It just runs the circuitry, and whether or not they're negative or positive doesn't matter to this instruction. And then it's an important detail to add to the bottom that if you use mol s, the negative and 0 condition flags are updated according to the result. So that's, I think, a good, thorough answer for that question. And I'm sort of pausing on it to give you time to catch up on that if you want to use something similar. But also you can see where I got it from, and then I just cleaned it up to make it read better as an answer. And then I thought I should, at the end, point out the extra detail about mol s, since that is different, which condition flags it would alter. Okay, so I went much slower on that one just so you can sort of see the whole answer come together and what I'm thinking as I do it. I would like to leave time to write myself a little program to try these things out, but we'll just see. Okay, so hopefully that's not too fast, but you say where I got those from. Okay, so show the signature of S-mol and then describe the operation of S-mol and S-mol S. So I'll be careful. I'm going to use a similar setup. So if I go back to my multiplication, here's the S-mol section. So here's the signature. So S-mol optionally has the S to set condition flags. It optionally has a condition code, so you can use it in an if-then block. This one's weird because S-mol is actually designed so that if you get a bigger result than fits in 32 bits, you actually keep both. You keep the extra bits. So this destination low is the bits 2 to the 0 to 2 to the 31st, and the destination register high is the bits 2 to the 32nd to 2 to the 63rd. Notice, by the way, with S-mol, these two source registers are not optional anymore. So you have two destination registers, and you have two source registers. So this is how ARM lets you deal with the situation where you're doing multiplication and it's not unusual that you get a much larger result than would fit in your source register. So if you imagine you were to multiply 4.2 trillion times 4.2 trillion, those are both 32-bit integers. They're never going to fit in 32 bits as a result. So what ARM does is it splits the two halves. And then I'm going to sort of be lazy about this, but so what do you do if your answers are split in two? You have to do programmer gymnastics to make that data work. We're never going to do that in this class. It's kind of beyond our scope. But if you are writing a program in ARM assembly where large values are being multiplied, then you would probably end up having to write software that would deal with the situation where two 32-bit values multiplied together and became large enough to need 64 bits to store it. So that's what this does. Fortunately, in our class, we're going to purposely avoid that situation and never allow ourselves to multiply values that would be that big. So that's how we're going to deal with it, is just avoid it. Which is not a bad thing to do, right? Why not avoid the situation that causes complications? So that's the signature. Let's go get, just checking the chat sometimes. Okay, so let's go get some words. So the basics of it is that S-mol multiplies two signed 32-bit values and produces a 64-bit result. Just remembering that you can't actually, there's no 64-bit anything in ARM. So to get 64 bits of result, you actually have to split it in half and store it in two separate places. I hope that makes sense without me dealing with that just a whole lot. I might bring up my calculator and show you what that looks like here in a second. Let me actually do that. Maybe. Programming mode, do I have 60? Okay, I do. So let me just show you on a calculator real quick before we go on how this 32, 64-bit thing works. Calculator. Okay. So here's my programmer calculator. I can put it down here. Okay, so on ARM, I need the calculator. I need to be able to see the calculator. Okay. So if you can see it on the screen here, my calculator shows 64-bit results. So here's 2 to the 0 bit down here. And here's 2 to the 63rd bit. So if I multiplied two large values together, two 32-bit values, they could easily spill over into 64-bit. So what ARM does is it takes the top ones, 2 to the 32nd to the 2 to the 63rd, and it stores those in one register, and the bottom ones, 2 to the 0th to 2 to the 31st, and store those in. So the result is split in two parts, and at that point the programmer then has to do some tricks to kind of merge that data back together if it's needed. We're not going to do that because it's beyond our scope, but I just wanted to show you a slightly better visual of what that might look like. So if that made sense, great. If it didn't, don't worry about it tons. We're not going to mess with that in this class because it would cause us pain. Okay. All right, there's the basics. I'm going to go back and get the extended description of SMOL. So the values in the two source operands, that's Rn and Rm, are multiplied. The high order 32 bits, that's 2 to the 32nd to 2 to the 63rd, are stored in the high destination, and the low order 32 bits, 2 to the 0th to 2 to the 31st, are stored in a separate register. So the two halves of the 64-bit result have been split into two separate registers. And then it assumes that Rm and Rn are both signed values. But that's why it says SMOL. So I'm going to take that stuff and enhance my answer with it. And then like I did before, I'm going to put a note here just to make sure it's clear that I understand what SMOL S does. And I'm just going to take the part that I think sort of explains that, just like I did before. So if I put the S on the end there, then the negative and 0 condition flags are updated. Okay, so you probably know where this is going at this point. Number 3, UMUL. So same idea. Notice that UMUL, I'm going to grab the signature. You might think of a signature, by the way, it's a function header, right? That's another word for saying a function header is signature. That's all that is. Okay, so UMUL is very similar. It splits a 64-bit result across two separate registers, which makes it a beast to program. But it does let you do multiplication with big values. So there's the signature. I noticed the same thing. The result is split in two parts. So you have to have two destination registers. I didn't write this, by the way, but you'd have something like this. Low bits go in R0, high bits go in R1, and then the two arguments maybe are R2 and R3. There's 4 registers required. Okay, So there's a signature. Now we'll do the same thing for explaining it. So umol multiplies to unsigned. So unsigned values this time. I'm going to grab this paragraph, just like I did before, that explains the argument. So the values in the two source operand registers are multiplied. The high order 32 bits are stored in this piece. The low order, that's 2 to the 0 to 2 to the 31st, are stored in this register. And then RM and RN, the two sources, are treated as if it's assumed they have unsigned values in them. And then I'm going to add the umol S detail, which I'm betting is the same. Yep, the N and Z condition flags are updated according to the result. Same thing. So that to me is a nice sort of clean answer for that. And I'm just letting a couple of lags drop in. There we go. When would the condition flags be updated when multiplying unsigned values? You could get a, I don't know when you get a negative, to be honest. I don't know what that would mean, but if you were to multiply something by 0, then the 0 flag would definitely be set. So that would be one that I could anticipate. I'm not sure why negative would actually be set. That's a good question. Why would negative be set? I don't know. How could that possibly be? 0, I can imagine. I'll have to look into that one and let you know, because I don't know off the top of my head why the negative would ever be set for unsigned. 0 I can imagine, because if one of the operands is 0, then you're going to get a 0. Let's see if I can quickly find the answer. Good question, and that's left for me to figure out before Thursday if I can figure out an answer to that, because I can't think of how that would, or why that would happen. So good question, and that it gives me a good homework problem to try to solve myself before Thursday. Can I answer the question of why would negative be set when you're multiplying unsigned integers? Seems impossible. It can't be overflow, because you can't get overflow by multiplying two 32-bit values and getting a 64-bit result. Yeah, so homework for me. Excellent question, though. Okay, so I will do my best to answer that question by Thursday. When is it safe to use the lazy mul? So remember, lazy mul is what I call it. That's takes two 32-bit values and gives you a 32-bit result. S-mul and U-mul take 32-bit values and give you a 64-bit result. So mul is riskier than S-mul or U-mul. So when is it safe to use them? And the answer is actually right down here on this page. So if you are certain that your multiplication is going to be in the right range for signed and unsigned integers, then it's safe to use mul. The author of this page misspelled the mul instruction. I'm going to fix that. But you use mul when you're absolutely certain that it can't happen, that you're going to overflow your result. Oh God, that made a mess. That made a mess that I'm going to have to clean up. That's unhappy business. Well, so it goes. right way to go. I'm just using the delete key here, by the way, to clean it up. Less than x, less than or equal to. I'm going to bump this down because it's getting hard to read already. All right, that wasn't that bad. For sign integer or I don't know if everyone else is having the same miserable experience as me. For unsigned. And I'm going to just do that to make it easier to read. Okay, but hopefully you get the point. You use mul when you're positive that you're not going to fall outside the acceptable range. And you can control that, right? You can control the data that your program is managing so that there's no two values when multiplied together in there that would ever overflow. Okay, so Brooksy also had that miserable experience. I just used the delete key to clean it up and then kind of separate it out just because I thought I'm going to take that comma off because I think it looked better without. So that one is acceptably readable now. But you saw where I got it. I just copied it off this page. Oh, wait. Then you can use the mul right here. That's misspelled, man. He put two L's in there, or she, whoever that was. Just going to fix that. Okay, there's the mul section. We're doing okay on time. I may not have time to do a test program, but we'll survive. Yeah, indeed. Okay, so I feel better. I didn't want to blame Linux. That just seemed kind of bizarre. I'm on a Linux machine, but it's just how they're the tooling they're using to present those arithmetic expressions. Poops in the clipboard. Okay, so that's the multiplication stuff. So now let's do division. This is going to be very, oh damn it. Sorry, I need to bring that up in a separate tab so I can flip back and forth. Because I don't want to lose all my carefully crafted answers. I've already done this before. Probably you could have guessed that. But these were all nice and clean. Okay, so SDiv. So now the division stuff. Same setup. So the signature, describe the operation, and then this one has an extra question on it, which is, does it set the flags? So here's SDiv, which is for doing division. In ARM, there is no mod, by the way. So there is no way to easily compute remainders in ARM. In Intel, it turns out that there is a way to easily compute remainders, but in ARM, there is not. So there are no mod instructions. But here's the signature for SDiv. And we'll notice there's no optional S, so there isn't even an option to set condition flags. We also notice, by the way, that all three register arguments are required. So that's important to note. Okay, Brooksy and Vince had that same problem. So hopefully you were able to just clean it up and that wasn't unpleasant on number 4, but wasn't super awful, I guess. Okay, so here's the signature of SDiv. And then we will describe the operation as we've been doing. So this is for doing division. Divides a 32-bit value into another, producing a 32-bit signed result. That was something that we could have anticipated because of the S. Signed values. There's no optional S to set the condition flags. That's not even an option. One thing to note here is that you can't overflow when you're doing division, because there's no way to divide you're always going to get smaller, right, when you do division. So it's never a worry that I have two 32-bit values and I'm going to get 64 bits a result. It can't happen with division. So these are pretty safe. And then right here, there's a note. The condition flags are not changed, and it's not even an option. I pasted without the. I'm dreading, by the way, more of those numbers. I hope there's no more of those in there, because I didn't like that. I'm feeling like this is a little bit sketchy. Let's see if we can get a little bit more verbiage. Yeah, let's grab this piece too. So the value in Rn, that's important actually. That's important detail to note as we're sort of gearing up to use these instructions. So the value in Rn, that's that piece right there, is divided by Rm. So Rn is divided by Rm. So the Rn would be the x divided by the Rm, which is the y. And notice there's no divide equals setup. All three pieces are required. All values are treated as signed. That's the S part. And then the remainder is lost. So that's important to note that you get no remainder. It just doesn't compute it. Okay, udiv, that's going to be the unsigned stuff, of course. So udiv, here's the signature. So I notice again, there's no set the condition flags option here. And then all three arguments are required. There's no curly braces. The only thing that's in curly braces here and in sdiv is the condition code, which means that you can execute it inside of an if-then block. But you might remember by now that all instructions can be executed that way in ARM. And thumb too, which is what our platform has. Okay, so now let's get the words. So I like these words. Divide an unsigned 32-bit value into another unsigned, producing a 32-bit unsigned result. And then I'm going to get the extra words in the little paragraph here that tells you some additional details that may have value. So Rn is the numerator and Rm is the denominator. So it's Rn divided by Rm, the result stored in the destination. All values are unsigned and the remainder is lost, just like it was with sdiv. And then there's the second part of the question. Does this instruction set the condition flags? And it says the condition flags are not changed. So I'm just going to take those same words, and that's also true for udiv. The next question is easy. Do they compute remainders? No. We just saw that twice. The remainder is lost. The remainder is lost. So no, they do not. So then the question becomes, well, then how do you get remainders? You do it by doing math, basically. And it would be nice to have an instruction to do the math for us, but you just do math. So before I do the answer, I'm just going to show you the math, and then we'll write the... So let's say you have z equals x divided by y. And I want a to store the remainder. So how do I get from z equals x divided by y to a remainder in a? Another way to think about this, by the way, is if I have, how many do I want? Let's say 24, 26. Let's just say I have 27. Sorry, I know I always use the donuts thing. I don't know if I told you guys this, by the way. I'm giving you a little bit of a breather while I set up for this. Um, we're in Arizona right now. Where we live in West Sacramento probably doesn't have it anymore because of what's going on, but they have a really good donut shop there, and that's a thing that I miss because all we have here is a Dunkin' Donuts, which is all right, but it's not the little local donut shop. So anyway, this example is in tribute to what I suspect will be a out of business donut shop whenever house arrest has been lifted. Okay, I have 27 donuts. How many dozen and how many left over? So if I wanted to compute that, what would that look like in high level? So the Z, so I'm going to change this. I will say the dozens equals total donuts divided by 12, which is the number in a dozen, and then the leftover equals what? So that's all we're doing is I'm just reminding you here that this is just math. That's all we're really talking about is that ARM doesn't do this math for us. We have to do the math for ourselves. So let's just set up a scenario and do the math and then translate it into assembly. So if I start with 27 total donuts, how many are left after I take all the dozens out? That would be the remainder, right? Well, what it would be is, so we have 27. That's going to give me 2 dozen, right? And then I need to figure out how many is left over. I want to undo that. So let's leftover equals question mark. Okay, so dozens would be the total donuts divided by how many donuts in a dozen, and then the leftover would be it would be 12 times the number of, it'd be the total minus the dozens times 12. That's sort of just the long form math of it. Hopefully that makes sense. So the total, which is 27, minus how many dozens would I have gotten is 2 times 12. So this is sort of the actual math of getting a remainder. You know this, you haven't thought of it this way in a long time, perhaps. So 27 minus 2 times 12 would be 27 minus 24 would equal, would give me 3 left over. That's the math of it. So that's all this question is really about, is how do you do that in assembly? So the leftover equals the total donuts minus the dozens times the 12. Now if we change this to be per dozen, then we get it more like a math per dozen. We get it more like a math equation. So this bottom piece is just, okay, so now let's just translate this basically. So we're going to say that dozens is R0, total is R1, per dozen is R2, and leftover is R3. Hopefully I don't mess this up. I'm about to mess it up. So I'm just going to translate that into registers, and then I'm going to translate that into assembly code. So the values are signed, it tells me. So all that really means is that I need to use sdiv and possibly small. So I'm doing signed division. I'm going to say the number of dozens, which I want to be in R0, equals the total, which is R1, divided by how many donuts per dozen, which is in R2. That's the initial expression. So now R0 knows how many dozen there are, but what I don't have is how many are left over once all the once I've taken all the dozens, boxed up all the dozens, what's left over. But R0 is now the dozens. Okay, so now we have to do a little bit of trickery. So we need to handle this expression, but notice this expression is actually two expressions. This one and then this one. And you can't do two expressions inside of, at least not yet, in ARM assembly. So we have to break this part out. So these are signs. I'm going to do an SMO. And I don't really have a register to represent this piece yet, so I'll just use R4 for that. So just for this piece, I'm going to get R4 as the result of multiplying R0, that was the dozens, by the per dozen, which is R2. Let me space this over so that makes sense. I'm kind of ignoring these registers, by the way, R1 divided by R2. Oh, hey! Store the result in R4. I don't know that I care about that. But we can always just fix that to match the question. Okay. Hopefully you saw where all that came from so far. So now I've done this piece. So now I have that whole dozens times donuts per dozen is in R4. So R4 is dozens times the per dozen. So now I need to do this part. And it tells me to leave it in R4, so all right. So I'm going to subtract. I want to leave the result in R4. I am going to subtract total donuts, which is R1, minus the dozens times, which is the old R4. So hopefully you know this. What is R4? So R4 at the end of that is the what's left over or the remainder, which is what we wanted. So that is very simple math. It just looks very intimidating in assembly. That's how you get R4 to be the remainder of dividing R1 by R2. But I did the whole donuts thing just because for me that helps sort of track the problem. Hopefully that helps you track the problem a little bit as well. I'm going to leave all that crap there just so you have it to read and it's in the video. But anyway, all this is just to illustrate what we were trying to do, which is divide R1 by R2 and figure out what's left, what's the remainder. So another way to say that is that this is how you do mod in ARM. You run the division and then you break the problem apart until ultimately you can get back to the remainder piece. Okay, which kind of sucks. So it turns out that ARM made an instruction that solves this problem. Hold on. Oh, unsigned. All right. Let's do this unsigned first. That's just unsigned. So, okay, there's unsigned. Just to remind you, by the way, notice that the div and the mul are unsigned, so you need to be careful about that you're not mixing the two, unless you mean to be, but normally I don't think you would. So number 9 is super easy. Okay, just letting everybody breathe. Sorry, I was over there trying to answer Vince's question and trying to give you some hints about how you might search it, but I haven't found anything that's useful for that just yet. Okay, so there's the unsigned version. I just changed sdiv to udiv, and I changed smul to umul so that we're doing all things unsigned. Okay, the last one though. There is an instruction that makes this slightly less painful, called MLS. So if I go back to this division page, I think, is MLS in here? Yeah, so if you go way to the bottom of this division, there's MLS. It's really, really weird at first to understand what's going on. MLS, what it does is it multiplies two 32-bit values in registers, subtracts that result from the value in a third register, and stores that in a fourth register. And I've never seen the word somewhere. Oh yeah, minuend before. But it doesn't really matter. These are the two that are multiplied together, RM and RN. So I'm going to take this signature and then I'm going to flesh out my solution this way. Unsigned. Okay, so I know that this thing is involved because the question tells me to solve it this way. So what I'm telling you here is that this is kind of as close as you get to doing mod in R. So I'm going to take my same setup, unsigned, so udiv R0 gets the result of dividing R1 and R2. Okay, that's all fine. Now I need to set this thing up. So this thing actually does capture, what this thing really says is RD equals RA minus RN times RM. And doesn't that look familiar? So it turns out that, but why they just didn't do a mod, I don't know. I would be really happy if they would just make a mod. But anyway, they have this instruction, which is probably useful elsewhere. Certainly useful here. This instruction is the same thing as what we did with our little leftover calculation, except for, if you remember before, this leftover calculation took two instructions, a mul and a sub. So what this is telling us is that now instead of two instructions, we can do that whole bit in one instruction. So not going to worry about the condition code. I want the result to go into R4. All right, now here's the tricky part. Who gets multiplied by who? I want to multiply R0, that's the dozens, times what is that? R2, which is the per dozen, I believe. Yep. And then I want to subtract, I want to say this RA minus R0 times R2. So this is the total donuts, which was in R1. So what this is saying is R4 equals R1 minus R0 times R2. Why those are all in a crazy order, I don't know. I assume it has something to do with making the circuit and the assembly match more efficiently or something. But anyway, that's how this one works. RD equals RA minus RN times RM, and they're out of order. You just have to be mindful of that. So R4, which is where we want the result, equals R1, the last argument, minus the two middle ones multiplied together, which is what we were doing before. So that's the answer. I'm gonna move these and then leave my little notes for you. I'm me go back and get the signature just as a reference point. So that kind of went back to my little donut problem as a reference. And then this is from reading the description of MLS, how the setup is meant to work. And then here's an application of it to get my leftover donuts. And I used up all of our time. I'm frustrated I don't know the answer to that UMall question yet. So that's the whole thing. You know how multiplication and division work. You know how to get these remainders. It just looks terrible in assembly. I know it does. We're going to practice this a handful of times on Thursday when we build that lab. So I'm going to pause here for a second, and then I'm going to go look at the lab just to give you a heads up about what's coming. Okay, so let me let's look at the lab real quick, which hopefully you made a wise choice here, because if you look at lab 13 diagram, this is the same as lab 11. So, okay, my camera is not showing any sign of life right now. Okay, now it did. Okay, so I just left this intact. I was just showing you it's the same circuit as lab 11. So I disconnected it, and people who send in late labs, I have to like reconfigure the board a little bit sometimes. And so here's the state of my board after lab 12 grading. So I'm gonna have to reconnect these wires, which I will do right at the start, but I'm gonna go fast about that. So your best way to prepare is to reconnect this circuit, or if you have to, rebuild it from lab 11 for our lab work on Thursday. I think this is the FizzBuzz program, if I remember correctly. Let's see. Yeah, this is the FizzBuzz program. So we're gonna cycle a series of values through here with the counter, just like we do with FizzBuzz, and then make the light change for fizz, buzz, fizz, buzz, fizz, buzz, fizz, buzz, or we're gonna show the value. So this will be a binary display that does the FizzBuzz problem. If you don't know FizzBuzz, go look up FizzBuzz. And there's a whole bunch of websites. There's Wikipedia about it. Coding Horror has a famous article about it. This is a classic computer science problem. I think it's largely an urban myth, but that's the problem that we're doing in assembly with ARM on Thursday, is FizzBuzz. I know you can't really see this, but it doesn't really matter. I was just showing you. I have to reconnect my circuit to my board. Okay, that's what I have for today. I'll wait around and see if you guys have any questions. And then as you're logging off, I'll just say have a nice rest of the day today, have a nice day tomorrow, and hopefully you'll find Thursday's lab entertaining. I'm looking forward to it because it just feels kind of cool to do assembly LED FizzBuzz. Thanks, Vince. You too. Does everyone feel? Hopefully, you feel good to go. And you can always ask, of course. And I will also, as always, be here at 10 a.m. on Wednesday. So if there's a stray question, you can always drop in on that. I'm usually alone, save one or two people from Program and Algorithms 1. So Wednesday mornings are good if you have a stray question to ask. Okay. You too. Thanks all you guys for being here. Appreciate it. It's be a lonely business if there's no one out there showing a sign of life. So I really do appreciate that you guys get up and spend an hour watching me. And I have homework, which is to figure out what in the hay does UML do when it sets the negative status flag. So I will do my best to find that answer for Thursday. Anyway, so see you guys later.